Yep, researchers in a lab taught a tiny clump of neurons to, in a sense, play this video game. But it's more than just a game. Some believe merging biology with computing could upend our approach to artificial intelligence. AI is a massive, often volatile, global market, with people looking all over for a competitive edge. In 2025, private sector companies teamed up to invest more than $500 billion in AI infrastructure alone. But what if the building blocks of that infrastructure include living human brain cells with the promises and challenges of our own biology? Sounds like sci-fi, right? Well, we're kind of on our way.
Science fiction talked about this.
I love thinking about the Hollywood stuff, like, are we really computers? Are computers really human?
My life has been focused on how can you elicit intelligence from brain cells in a dish. Trying to ask the question, can you interact with a bunch of brain cells in a dish and get them to do anything useful at all?
Brett and his team started by growing a layer of 800,000 neurons on top of a silicon chip. That's about the size of a small bumblebee's brain. And since neurons in our brain naturally communicate using electrical impulses, the researchers could both send and receive impulses between the neurons and a computer hooked up to a silicon chip. To translate the Pong game into something this clump of neurons could sense and control, the chip is divided into 3 sections. There's one larger sensory section, which sends electrical impulses to the neurons to represent aspects of the game, like where the ball is. There's also 2 motor sections. If neurons send impulses in this one, the paddle moves up. If neurons send impulses in the other, the paddle moves down. The chip acts as a communicator between the neurons and the game, but it still doesn't mean that these neurons would want to play the game.
Why would a bunch of cells in a dish actually change their activity in any particular way? There's no Pong playing gene that exists in brain cells to make them want to play the game Pong.
So the researchers tried to give the neurons incentive. Every time the brain cells missed the ball with the paddle, the researchers stimulated them with chaotic and unpredictable bouts of electricity. On the other hand, when the neurons successfully hit the ball, they received predictable stimuli from the researchers. Within minutes, the neurons started hitting the Pong ball more consistently. Why did it work? One possible explanation is a theory called the free energy principle. It suggests that almost all things in nature, even as small as the dish brain, are constantly trying to perceive and understand their world and minimize surprise.
If you can't predict what's going on in the world, if you can't say, if I reach for a glass of water, I'll successfully pick the water up, it's very hard to survive.
Dishbrain was a proof of concept for this larger idea of biocomputing, also called organic computing, biological hardware, and perhaps most vividly, wetware. Dishbrain made a splash, so big in fact that another team of scientists tried the same experiment using hydrogel, a non-living, soft, flexible substance similar to Jell-O. The hydrogel also learned to play Pong. So the question became, what can neurons do that other substrates can't? How much computing abilities can they provide? And frankly, can they make any money now? When they got their neurons to play Pong in 2022. They called it Dishbrain.
Yeah, let's just set up and see how it goes. Maybe we'll all be in for a surprise.
Quick timeout. Before we go any further, it might be worth understanding why companies like Cortical Labs are blending living neurons with synthetic systems. Compared to traditional machine learning, brains need far less training data to understand real-life environments and new situations.
So what you're seeing here is we're investigating, can neurons actually distinguish between different handwritten digits? And we want to see, can the neurons behave in a way that says they recognize that all of the 6s look like 6s, all of the 4s look like 4s, and so on. Anything with biology can learn to navigate its environment incredibly quickly, incredibly efficiently. And we've had to learn to do that through evolution, otherwise we died.
Supercomputers like this one can be 1,000,000 times more powerful than the fastest laptop. But both supercomputers and AI run on the same basic technology, silicon chips.
There's never been a focus like there is currently on the chip industry. People have realized that chips are the heart of everything, that this fundamental change to the economy that's being promised in the form of AI depends upon semiconductors, depends upon their rapid development, and depends upon an ever-increasing supply of them.
For over 50 years, we have been creating better chips by packing more and more transistors inside one integrated circuit. The transistors are on-off switches, the physical manifestation of ones and zeros. And we've gotten faster and faster by going smaller and smaller. Over the last 6 decades, we've been trying to double the amount of transistors on an integrated circuit every 2 years. This is the heralded Moore's Law, observed by this guy back in 1975. Today, a phone's processing chip contains billions of transistors, and those transistors are so small, they're just a few nanometers apart in places. But, as our good old Intel co-founder, Gordon Moore, observed, this steady march of progress also has an endpoint.
You're creating a chip, a three-dimensional circuit, by depositing layers of material on a disk of silicon. Some of those layers now are 1 atom thick. Guess what? When you get to 1 atom, you can't go any thinner.
So, we have a problem. So neurons might help solve some problems, especially around energy. Our brains are much better and more efficient in similar tasks to AI. For example, a supercomputer must consume up to 40 megawatts of power to function. Our brains run on just 20 watts. That's the difference between a couple of LED light bulbs and thousands of homes. Our brains are also powerful, with about 86 billion neurons that form over 100 trillion connections to each other. And with cells, the distinction between hardware and software isn't quite as well distinct. They're dynamic and intertwined. The cell's actual structure can change and mutate too.
Because of the way that computer chips are organized, they have limited logic functions. They tend to want to do things one thing after another. That's what they're good at, that's what they were designed to do. Human brain doesn't work that way. The human brain is kind of a lattice structure of interconnections where information flows in sort of different ways and different points. So the limitations of bio is that we're just at the very beginning of it.